The purpose of this lab was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. In this lab, we were given a video to observe the values of calibration length, time between video frames, and relevant masses needed for calculation. We were to create a model to predict the swinging, oscillating motion of the mass using Newton's second law, and then compare the predicted motion to the motion observed in tracker in the same graph. Using the energy principle, we were also able to show the changes in kinetic energy, gravitational potential energy, spring potential energy, and the total energy. It was found that the model was accurate to a degree, but there were deviations in predicted x and y positions, as no dissipative forces were included in the model predictions. In this lab, we were given a video to observe. The calibration was set to 0.7 meters, which was also given. The center of mass was found in each scene in order to get values for the x and y positions, and was started just as the mass was let from rest. In the computational model, the observations found in tracker were used to set the initial conditions. The mass was given to be 0.402 kilograms. The initial position of the mass was given from the x and y positions corresponding to when time equaled 0. The spring constant, the relaxed length, and the period were then all calculated from observed positions. The period was calculated as an average in order to get the most value to find the spring constant. For the rest of the predictions, Newton's second law was used to update the gravitational force, the spring force, the net force, and the velocity and position. It was then important to add code in order to update values that are used in calculating the spring force, as the spring force changes with changes in position. Finally, the energy principle was used to find the kinetic energy, the gravitational potential, the spring potential, and the corresponding changes in those energies, along with the changes in total energy. Plotting the model predictions and the observed positions on the same graph, it can be seen that there is some deviation from the predicted position. The observed positions are seen to be of less value than the model predictions. While there are errors such as not accurately finding the center of mass in each scene, the difference in the model and the observed positions can be largely due to not including dissipative forces in our model. Dissipative forces are forces that reduce energy and do not return it into the system, and include forces like air resistance. In our graph of the energy, the yellow line represents the change in total energy. This line is shown overlaying 0, allowing us to conclude that the change in total energy is equal to 0 and satisfying the energy principle. It also shows no significant interactions with the surroundings. The average period for the x direction was found to be 1.657 seconds. The x direction period can be described as the time it takes a mass moving in an arc-like shape to complete one full swing. The average period for the y direction was found to be 1.51 seconds. The y direction period can be described as the time it takes a mass oscillating up and down to complete one full oscillation.